So data insight speak theory is to gather all the high-profile speakers from all the area related to data science. I'm immensely grateful to Axel, who is our chair to today's event.
Thank you very much, EK. I'll keep this very brief as well. I'm delighted to be here, to have been asked to host the second in this series. I've got to admit, I was a little bit apprehensive when I was asked to chair this particular event. After all, what is a journalist who's covered politics and business for most of his life really know about how physics and maths can help explain the occurrence of improbable events. Then I started reading the book, and I could not put it down. Rich with colourful anecdotes as a means of explaining complex concepts that are quite hard to grasp for people like me. So that was perfect. I saw this quote just the other day. David Hand has written, he said, a superlative introduction to critical thinking, accessible to everybody regardless of mathematical ability, and essential if your probability of taking a university-level maths class is less than 0. Just to add a couple of feathers to David's cap, as well as his role here, he's the former president of the Royal Statistical Society, and I find this very interesting, and hopefully this is something we'll talk about afterwards as well, chief scientific advisor to Winton Capital Management, the hedge fund. Ladies and gentlemen, David Hand on why incredibly unlikely things keep happening and why we shouldn't be surprised that they will continue happening. David.
So in 2012, I attended the Royal Statistical Society's conference in Telford. I did what you do. I went up to the reception desk and said, "My name's David Hand." The receptionist looked at her screen and said, "But you've already registered." After a moment's sort of existential doubt, I said, "No, I haven't." She looked at her screen again and said, "Oh, I see what the problem is. There are 2 David Hands with us this week." Then she asked me a question which at the time I'd never been asked before. She said, "And which one are you?" I then gave one of the only 2 moments of quick thinking in my life, I think. I said, "The real one, of course." She wasn't so impressed. She just sighed and said, "They all say that." Anyway, the point of this little anecdote is that it was an extraordinary coincidence. Something amazing seemed to, bumping into another person with my name. My name isn't John Smith or something like that, not very common. So I was stunned. And similar things may have happened to you. You might, for example, have thought of someone just before they phone you, or bumped into an old friend in a strange town. You're on holiday in Paris and you find your neighbour or something like that you bump into. Or meeting somebody who's got the same birthday as you. Or perhaps finding that the number of your house or your PIN number or your car registration, your car number, whatever, keeps cropping up in different circumstances. Things like that. These sorts of questions, these sorts of events, might make you think that something funny is going on. They might make you wonder exactly what's happening. They might make you think there's something about the universe that we don't understand, or that perhaps we have misunderstood the laws of cause and effect. And thinking that, asking these questions, have we misunderstood the laws of cause and effect and so on, is not a silly thing to ask. A great many major scientific breakthroughs, relativity comes to mind, have arisen because people spot something anomalous or think that things that we can explain don't quite work. So it's not silly to think this. Or you might think perhaps there's something in exerting an invisible influence on our lives. Now, what I'm going to do is argue that the answers to these questions is yes, there is, not exactly the laws of cause and effect wrong, but it's perfectly legitimate and sensible to ask these. So in a way, the answer to these questions is yes. But something which is exerting the force, if you like, on us isn't some mystical super being or force. It is, in fact, a consequence of solid mathematics, solid probability theory. but looked at from a different, rather unusual perspective. And this is the perspective that I've called the improbability principle. And in a sentence, the improbability principle says extremely improbable events are commonplace. That's one way of just expressing it. And when you read that, you think, well, that's clearly nonsense, isn't it? By definition, extremely improbable events can't be commonplace, or they wouldn't be extremely improbable. So it looks like there's a contradiction in this assertion, in this encapsulation of the improbability principle. And what I'm going to do in the rest of this talk is basically try to convince you that it isn't a contradiction. You should expect this sort of thing to happen, and that the improbability principle makes sense. Now, the improbability principle isn't a single law like Einstein's E equals mc squared. It is, in fact, a set of 5 laws. It's like Newton's 3 laws of motions or the 4 laws of thermodynamics. It's a group of laws which sort of intertwine, they braid together to form this rope of the improbability principle. And here they are, the law of inevitability, truly large numbers, selection, probability lever, and near enough. And what I'm going to do in the first half of the talk is go through these to illustrate them. I think if anybody else was trying to sort of form an improbability theory like I've done, they might come up with different laws. I think the first 2 or 3 would be the same. The other ones might be formulated, phrased slightly differently, but they would cover the same space that I've covered in these 5 laws. Like you can express the 4 laws of thermodynamics a different way, but cover the same space spanned by those 4 laws. This is the way I've done it. And the first couple of laws will be pretty obvious, and gradually, as I work through, they'll get more sophisticated. And I was going to say abstruse, I mean abstract, of course. Anyway, let's start with the first. This is the simplest law, the law of inevitability. You can express these laws in different ways. One way of expressing this is that something must happen. Let me show you what I mean. If you flip a coin, it's going to come up heads or tails, or perhaps end up leaning against a fold in the rug, or slip down a crack between the floorboards, or something like that. I'm going to call all those other things other. So it's got to come up heads or tails or other. There are only 3 possibilities. It is inevitable that one of those 3 possibilities will come up. That's the law of inevitability. One of those 3 must happen. Here's another example, a rather less trivial example. In any given lottery, there's only a finite number of lottery tickets. In the UK, we have what's called a 649 lottery. It means you've got to choose 6 numbers out of 49 numbers. So there are about, you do the maths, there are about 14 million different possible lottery tickets you could buy. And it is guaranteed, it is inevitable that one of those 14 million lottery tickets will come up. It's the law of inevitability. Something must happen. One of those things must happen. So far, pretty trivial, I'm sure you'll agree. Let's build on this second example. I'm going to describe a fairly well-known example called the case of the International Lotto Fund. And the situation is this. On the 15th of February 1992, a Virginia state lottery had rolled over several weeks, and the jackpot was $27 million. It's a 644 lottery. You have to choose 6 numbers out of 44 for each ticket. And you do the maths, and you find that there are 7 million different tickets, not 14 million like in the UK, 7 million different tickets. You can probably see where I'm going with this now. Each of them has got a 1 in 7 million chance of being right. But, of course, if you bought all of them, all 7 million, which would only cost you $7 million, you would be guaranteed to hold the winning ticket. So you would be guaranteed to win the jackpot. And this is exactly what a group called the International Lotto Fund did, led by a man named Stefan Mandl. He put together a consortium of 2,500 small investors, each investing $2,800, international from all around the world, and bought up, set out to buy up all the tickets. But a number of things could go wrong with this. First, there's the sheer logistics. You've got to buy 7 million tickets in a week between one draw of the lottery and the next, because you've got to wait for it to roll over that. So you've got a few days to run around buying 7 million tickets. In fact, as you can see from this slide, they didn't manage to do that. They only managed to buy 5 million tickets. I have this picture of them with their 5 million tickets, tipping them out into a giant pile on the floor and then going through them, biting their nails, hoping they've got them. There's a 1 in 4 chance that they wouldn't have the winning ticket. I'll relieve the tension now by telling you that they did have the winning ticket. But that's not the only problem. Maybe others would win the ticket. Maybe Mrs. Smith down the road buys 1 lottery ticket each week, and by luck, this week, she happened to also get the jackpot winning ticket. So they'd have to split their $27 million winning. maybe even split it between more than two people. So that's a risk. And then there's also a legal challenge. The fine print of this lottery said that you have to print out your ticket at the same place you pay for it. And they hadn't done that. They'd done it in some cases, but they'd also bulk purchased a lot, writing a large check for $3 million and having lots printed out elsewhere. In the end, the operators of this lottery said, OK, we can't prove that you didn't print out the ticket at the same place you paid for it, so we'll let you have the money. So this really happened. In fact, it happened more than once. It also happened to the Irish National Lottery. And in fact, the French writer Voltaire originally made his initial fortune doing this sort of exercise. He was friendly with a mathematician, and the two of them devised a scheme which did this. So it's got a reputable history. OK, that was the law of inevitability, a very simple law. Something must happen. If you make a complete list of all the possible outcomes, one of them's got to come up, inevitable. Let me move on to the second law, the law of truly large numbers. In statistics, we have something called the law of large numbers, which basically says if you take an average of a sample, the larger the sample you get, so the average converges to a particular fixed value. This is different. This is the law of truly large numbers. And one way of expressing this is that with a large enough number of opportunities, any outrageous thing is likely to happen. You can express it in other ways, but I'll show you what it means. And let me kick off with an example involving lightning. Worldwide, I'm going to come back to lightning later on, but worldwide, the chance of being killed by a lightning strike is very small, 1 in 300,000. You can all relax. 1 in 300,000. But there are 7 billion people in the world, a truly large number. So if you do the maths, 7 billion people, each with a very, very small chance of being killed by a lightning strike, you find it's infinitesimally small that nobody in any one year will be killed by a lightning strike. And in fact, about 24,000 people each year are killed by lightning strikes. The numbers here are ballpark figures, okay? If you look at other different sources, you will find different figures. These are sort of order of magnitude, really. The reason that it's difficult to get exact figures, well, there are things like if you're under a tree which is struck by lightning and it falls on you and kills you, are you killed by the lightning strike? There are ambiguities, but these are the sorts of numbers which we're talking about. They're about right. I want to illustrate something here now. Keep your eye on the bottom right of the screen. Nothing much happened. Oh, there's a man coming in. And he's been struck by. And let me relieve the tension by telling you he is not killed. He's just been stunned. In a moment, you'll see him rub his head. It obviously wasn't a very pleasurable experience. Sit there for a bit and then wander off. So he was unlucky. He was struck by lightning. In fact, I'm very unlucky. Struck by lightning when he was walking in front of a camera. Actually, thinking about it, maybe he wasn't unlucky. There's an old saying, isn't there? Lightning never strikes twice. He was struck by lightning. He wasn't killed. Luckier than all of you who may be killed the first time you're struck by lightning. Oh, look, he's walking off, rubbing his head, feeling a bit unsure of himself. But lucky, because lightning never strikes twice. He isn't killed there either, so you can relax. OK, so this is the law of truly large numbers. Here is another example. The Bulgarian state lottery is called the Tantalizer, and on this date, 6th of September 2009, these numbers came up. And they're pretty odd numbers. There's a consecutive pair, 23, 24. In fact, consecutive pairs quite often, if you look at the figures. People underestimate how often that happens. And they're all digits from between 1 and 5, so maybe very small. Perhaps those are odd. But that's not what I want to draw your attention to. What I want to draw your attention to is that the next draw of the lottery, these numbers came up. Extraordinary coincidence. So much so, it caused something of a media outcry over here, but especially, of course, in Bulgaria, where the sports minister ordered an investigation. I am always intrigued by why a sports minister is involved with this. I can't come out for a drink tonight. I've got to train for tomorrow's lottery. It doesn't seem to really... Anyway. But the law of truly large numbers says we should, there are a lot of lotteries going on. We should expect this sort of thing to happen. And the Bulgarian lottery is a 642 lottery. And if you do the maths on that, it turns out it's more likely than not that some 2 draws will match if you keep taking 2 draws per week like they do for 26 years. They may not be consecutive draws, but some sets of 6 numbers will match. It's more, probability is greater than a half that they will match. And in fact, if you think of the number of lotteries which go on around the world, and there are indeed a lot of them, you'd expect to see duplicate sets of numbers, even on consecutive draws like we just saw. In fact, it would be amazing, the law of truly large numbers, there are so many of these things going on, draw after draw after draw, lottery after lottery after lottery. Amazing if we never saw such repeats. And so you won't be at all surprised to see that in this Israel lottery, on these two dates, the same numbers came up. And you won't be at all surprised to hear that in the North Carolina Cash 5 lottery, on consecutive draws, these came up. The law of truly large numbers says we should expect these sorts of things to happen. The law of truly large numbers produces also... I like lotteries to talk about the improbability principle because it strips away a lot of the ambiguity and uncertainty of human life and communication. I can focus on the numbers, and people know about lotteries. So here's another lottery surprise. This woman, American woman, bought tickets with the winning numbers for both the Massachusetts lottery and the Rhode Island lottery. Excellent. The trouble is that the numbers she bought for the Massachusetts lottery were the winning numbers for the Rhode Island lottery and the other way around. Now, if there's anybody who thinks there's somebody up there with a particular malicious sense of humour manipulating, it must be poor Maureen Wilcox. Okay, so my third law is the law of selection. And one way of putting that is you can make things as likely as you want if you choose after the event. I'm going to tell you a couple of stories to get this going. One which you'll probably be familiar with. You're walking along a country lane and you come across a barn. And in the side of the barn you see lots of painted targets with arrows sticking right in the centre of them. And you think, wow, this guy is a really hot archer. And then you carry on walking along your country lane. You turn back to look at the other side of the barn and you see a lot of arrows sticking in the side of the barn and a man with a paint pot drawing targets round them. Actually, that's not such a far-fetched thing. We're sort of in the time of 100-year anniversary of the First World War, when aeroplanes were starting to be used in war. And one of the weapons they were experimenting with was dropping bundles of pencil-sized metal darts on enemy troops. And to understand how effective this weapon was, they needed to understand how the darts spread out after they'd been dropped. So they would carry out some experiments. They would drop them on a field, then they'd go around putting squares of paper to mark out so they could see how the darts spread out. In one case, they were doing this when a cavalry officer rode by and asked them what they were doing. And when he was told that in the centre of every square there was a dart, he said, "My God, I didn't think it would be so accurate from an aeroplane." So this is not so far-fetched. Here's another example, a personal example. When I was young, I was really impressed by how food producers could produce jars of whole walnuts. Because when I try to get a walnut out whole, I'd put it in the nutcracker, gradually increase the pressure, and then suddenly crack, and I'd end up with bits of broken nut and shell all over the floor. About 1 in 10 times I'd get it right, but I wasn't very good at it. And I wondered how the manufacturers could clearly do it every time, because they could produce jars of whole walnuts. And then I discovered they were no better than me. They are a little bit better, and they have ways of softening the shells, but I won't let that interfere with a good story. They were no better than me. They could get it right only 1 in 10 times too. But what happened was, whenever they got a whole walnut, they'd put it in a jar, and when the jar was full, they'd stick a label on it, whole walnuts. The others, they'd put in at the bits, they'd put in a jar, stick a label on it, walnut pieces. And I only saw the whole walnut jars. The law of selection. In both of these examples, you're selecting the data after the fact. You can make the probability that the metal darts will go in the centre of the pieces of paper, or that you can produce jars of whole walnuts. You can make it probability 1, because you're selecting after the fact. Here's another little example. Jean Dixon was a very eminent American psychic, and here's one of her predictions. 1956, 4 years before Kennedy was elected, she published a prediction in this magazine that in 1960 the election would be won by a Democrat who would then be assassinated or die in office. That was her prediction. Pretty good, you might think, until I tell you about some of her other predictions. Here are a couple. Someone from the Soviet Union would be the first to walk on the moon. World War III would begin in 1958. Now, she does this, and her name has been attached to it by using 2 of the laws of the improbability principle. One is make enough predictions, the law of truly large numbers. Make enough predictions, some of them are going to be right. And of course, select those. Tell people about the ones you got right. Say, hey, 4 years ago I predicted this would happen. And of course, people will tend to remember those anyway. Why should they remember all the predictions you made which didn't come true? This prediction here, in fact, wasn't so far-fetched, wasn't so good, if you like, as it might seem, because let's face it, who's going to win the presidential election? Well, it's going to be a Democrat or a Republican, right? Probably. And it turns out that 8 out of 44 of the US presidents have died in office. So it's not as impressive as it at first seems, which is another way you can become an eminent psychic. Okay, here's another example of the law of selection. A couple of journalists published a paper, in fact, a series of papers in the Wall Street Journal, in which they pointed out that some directors of companies had been extremely lucky. These are share prices for a number of shares, and the sort of targets, which I hope you can see on here, are the dates at which the directors had been awarded shares. And let's take the first one as an example. The director was awarded shares here, and immediately afterwards the share price went through the roof. My God, wasn't he lucky? Any other time he wouldn't have made half as much money. Threlfall and Bandler went through lots and lots of these share prices and discovered there were lots of situations like this, or quite a few situations like this, where the directors seem to be incredibly lucky. Now, the law of selection can apply in two ways here. Threlfall and Bandler looked at a lot of cases. Maybe they just pulled out the ones where this has happened. In their probability calculations, they took that into account. And the chances of the directors being this lucky were very, very small, 1 in 200 million, 1 in 300 billion, incredibly unlikely. In my book, I talk about something called Borel's law, or Cournot's principle, which basically says events which are this unlikely, you wouldn't expect to see them in the history of the universe or whatever. I discuss that and relate it to the improbability principle. But there's another way the law of selection can apply here. And this is, of course, that if you can decide after the fact when you were awarded the share options, you can make the probability that the share price will subsequently rise as high as you like. So if you're here and you're asked, when were you, or at least you're given the freedom to choose when you were given the share options, you would choose there, and the price, you'd make a fortune. And people are serving and have served prison time because of this. Threlfall and Bandler were right, this was fraud. But it's the law of selection. They were allowed to choose after the fact, making probabilities as near one, as near certainty as they wanted. So here's my next law, the law of the probability lever. It says slight changes can make highly improbable events almost certain. That's one way of putting it. So back to lightning. About 100 people get killed by lightning in the US each year. Now, you will know that the population of the US is 300 million. So the probability of getting killed by lightning in the US is about 1 in 3 million. But I said earlier on, worldwide, it was about 1 in 300,000. So in the US, it's only 1/10 of the worldwide chance of being killed by lightning in any one year. And why is that? Well, the circumstances are different. Slight changes. And in the US, for instance, buildings are better protected, lightning conductors. People spend more time in buildings than ploughing fields and things like that, agricultural workers. So the circumstances are different, which allows for this tenfold difference which explains this tenfold difference in probability. Let me give you some more lightning examples. This man, Major Walter Summerford, was struck by lightning in Flanders after the First World War. He's knocked from his horse in a field. His legs were temporarily paralysed. 6 years later, he'd moved to Canada, took up fishing, sitting under a tree, which was struck by lightning, paralysing his right side. 6 years later, walking in the park, and he was completely paralysed by a lightning strike. Whenever I talk about this, I'm reminded of that Monty Python film, Monty Python and the Holy Grail, the Black Knight. He's had his arms and legs chopped off. He's hopping around saying, I've had worse. And I feel this guy is rather like that. You will be, I was going to say disappointed, but perhaps relieved to hear that he died 2 years later, not from a lightning strike. But to rectify the oversight, 6 years after 1930, his gravestone was struck by lightning. Let me tell you about another man, Roy Sullivan. He was struck by lightning as well. 1942, lost his big toenail. 69, his eyebrows. 1970, his left shoulder was seared. 1972, his hair was set on fire. It regrew, but unfortunately the next year it was burnt off again by another lightning strike. 1976, his ankle was injured. 77, his chest and stomach were burnt. Now, what is it about this that has anything to do with the law of the probability lever? Well, this man wasn't an office worker. He didn't work in a safe environment like you. He was a Virginia Park Ranger. The circumstances were different. Just like Walter Summerford on his horse, sitting under a tree, walking in a field, and so on. The circumstances change, make it more likely. I mean, if you're a park ranger, maybe it's not so unlikely that you'll get struck by lightning 7 times. The circumstances are different. The law of the probability lever. Oh, here's another example of the law of the probability lever. This book, More Money Than God, by Sebastian Mallaby, is a history of hedge funds. He's writing about the year 1987, and he says, an event such as the crash wouldn't be anticipated to occur even if the stock market were to remain open for 20 billion years. Now, the universe is only 14 billion years old, so this puts it in perspective. Incredibly rare event, so rare you wouldn't expect it to happen. I'm going to move on 10 years, 1998. This book, When Genius Failed, is about the collapse of the hedge fund long-term capital management. And Roger Lowenstein says, figures implied it would take a so-called 10 sigma event. A 10 sigma event is another way of expressing very small probabilities, way out in the tails of distributions. I'm going to move on another 10 years, roughly. 2007, Bill Bonner in Money Week. Things were happening then that were only supposed to happen once every 100,000 years. Maybe that's not once every 20 billion years, but still a very small probability. At this point, I was tempted to move on another 10 years to 2017 and tell you about the crash of 2017, but I've decided to let you discover that for yourself, but don't say I didn't warn you. In fact, what I'm going to do is move on just 3 years to 2010. David Gartman says, what we witnessed yesterday was a series of movements of utterly unprecedented proportions, with currency price changes at the 6th, 7th, and 8th standard deviations from the norm. Highly improbable, way out in the tails. But I've just told you about a series of events at roughly 10-year intervals where these crashes occur. So rather than utterly unprecedented, you probably agree utterly precedented might be a better way of describing it. In fact, a couple of economists, Reinhardt and Rogoff, have written a book, quite a famous book, called This Time is Different, where they go back 800 years looking at financial crashes, which have occurred pretty regularly over that entire period. So precedented, rather. So what's going on? We've got lots of these things with an awful regularity occurring, but they're only, should it be expected to occur once every 20 billion years or whatever. What on earth is happening? Well, what's happening is the law of the probability lever. Many of you, most of you, I would guess, are familiar with this sort of stuff. The dark curve here is what's called a normal distribution, a distribution which is very widely used in statistics, in engineering, in science. The broken curve is a curve called the Cauchy distribution, and it's, when you look at this picture, it's very similar to the normal curve. In fact, had I used thicker lines to draw these curves, you wouldn't be able to distinguish between them. So it looks very similar to them. But the slight difference between them is, in fact results in this. The probability of getting a value out here in the tails for the normal distribution, the continuous line, is 1 in 10 to the 23. A very astronomically incredible. What's the weight of the Earth in kilograms is 6 times 10 to the 24 kilograms, so that puts it in perspective. But for this broken line, the Cauchy distribution, it's just 1 in 30. Very slightly different distributions, apparently, from this picture. But look at the difference. This is the factor relating those two numbers. It's the law of the probability lever. Slight changes in the distribution. Now, I gave you lots of calculations of probabilities. I quoted lots of things. Of course, people who work in the finance sector know that they shouldn't use a normal distribution because of this sort of phenomenon, but it's convenient to express probabilities in those terms. But this explains why you get these apparently extraordinarily improbable events happening with this awful regularity. Double-yolked eggs. Some of you may have cracked open an egg and come across a double-yolked egg. It happens about 1 in, I think I've got it up here, it happens about 1 in 1,000 times. So what's the chance, and this happens, I showed you a picture of it a moment ago, of getting all 6 eggs double-yolked in a box of 6? It's about that, 1 in 10 to the 18. Except the improbability principle. This comes in various ways. Younger hens are more likely to lay double-yolked eggs. So there's a sort of selection process going on here. Boxes of eggs tend to come from the same flock. They'll all be at similar sort of ages, for instance. So now we're shifting the probability of getting all 6 being double-yolked, not making it more likely than 1 in 10 to the 18. Also, double-yolked eggs tend to be larger, and therefore they'd be grouped by the machines as large and tend to be put in boxes together. And then the final thing, the law of selection. If you shine a bright light through an egg, you can see how many yolks it has, and then you can select them and put them in a box. so that you can get boxes of all 6 double-yolked eggs. So not as improbable as it first seems, using the different laws of the improbability principle. Okay, and then the law of near enough, the last one. And one way of putting this is events which are sufficiently similar are regarded as identical. So here's a little example. This man named Bill Shaw was, in 1986, he was in a train crash which killed 13 people. 15 years later, his wife also survived a fatal train crash that killed 10 people. How incredibly unlucky these two people were. Both should be. You want to avoid travelling with them. Actually, before I say any more, I should say that rail travel is very, very safe in the UK. 0.1 fatalities per billion passenger miles. So, you can go home by train after this. You're more likely to get killed crossing the road to the station than... But let's think about this. It wasn't Bill in both of these train crashes. It was Bill in one and his wife in the other. Had it been Bill in one and his brother in the other, or workmate or cousin or father or daughter or whatever, I'd still be standing here and saying, what an amazing coincidence. What I'm doing is expanding the range of possibilities so that I'm increasing the chance that one of these apparently separately highly improbable events will occur. Expanded enough, and you can make the probability as high as you like. Likewise, Bill and his wife weren't in these 2 train crashes on the same day or even in the same week or same year, 15 years apart. Had it been 20 years apart or 30 years apart, I'd still be standing here and saying, what an unlucky couple. So again, I'm expanding the range. I'm introducing more and more opportunities for these chances to occur, these rare events to occur. Events which are sufficiently similar are regarded as identical. Another little example. Sir Alister Hardy was a very eminent marine biologist, and after he'd retired professors do this sort of thing, he decided to investigate something he'd obviously been fascinated by all his life. In his case, it was telepathy. He was a very good scientist, so it was a very well-designed scientific experiment. What he had was, he's written a book about it, you can read about it if you want. He had 20 people looking at photographs or drawings, and he had 180 people separated from them, trying to discern through telepathy what they were thinking of and then sketch it. Now, there are a number of sort of scientific experimental design issues associated with this, which you will have already spotted, I'm sure. First, you have to decide, fundamentally, you have to decide when is a received image an exact match to a transmitted image. And they were aware of this. And in the book, there are examples of these things, and they've selected out a series of examples of direct hits when the received image was regarded as a perfect match to the transmitted image. And remember, there are 180 receivers, so we're getting, maybe it's not a truly large number, but a lot of opportunities for matches. So here are a couple of examples. This is one of the transmitted images. Now, you've probably already formed an idea of what you think that's a picture of. Here's one of the received images, which was regarded, 1 out of 180, which was regarded as an exact match. Now, superficially, it looks very similar, but if you look at the top, the receiver has kindly written a mountain and road. Now, I don't think that's an exact match. And here's another example. This is clearly Noah's Ark. That's the transmitted image, and this is the received image. Superficially, it looks the same, but the receiver has written railway station at the bottom. Oh, this is a personal little example, similar sort of thing. A few years ago, I attended a conference at St Anne's College in Oxford, and that's their crest. And at the conference, they gave us a notepad with the crest drawn on it, and here it is, the drawn version. And then sometime later, I was working at my desk at home, and this notepad was on my desk, upside down, so here's the crest. And I looked at that, and I thought, my God, it's Bart Simpson. And I started emailing a letter to the principal of St Andrew. I thought, better not do it. Now, it's not a perfect match. The eyes, there's something wrong with the eyes. But it was enough for me to think, what an extraordinary coincidence. But that's all it is. Okay, now, each of these laws can make apparently highly improbable events happen. But it's when they occur together that highly improbable, really striking things. I talked about the Jean Dixon effect, who used the law of truly large numbers and the law of selection. But here's another little example, and this isn't financial advice. Please don't take it away and work on this. And you may make a fortune, but you'll probably go to prison. Anyway, how to be a successful stock tipster. We're going to use these 2 laws. What we're going to do is predict whether the FTSE will go up or down. And what we're going to do is choose 1,024 unsuspecting victims, and to 512 of them, we're going to send a letter saying it'll go up. To the other 512, we're going to send a letter saying it'll go down next week. We're going to be right for one of those two halves. The half we get wrong, we're going to forget about. The other half, well, we're going to send half of them, 256 of them, a letter saying it's going to go up next week, and the other half is going to go down. We're going to do this for 10 weeks. At the end of the 10 weeks, you've got rid of 1,023 of them, but you will have one guy who has seen you make 10 successive perfect predictions of how the stock market's going to move. Clearly, you've got a superb algorithm. It really can, And at that point, you say, right, I'll tell you what will happen next week, but it'll cost you. And that's using the law of inevitability. One of those patterns of 10 ups or down movements must occur. There are only 1,024 of them, and you're selecting. So it's using it in a different way from the way I've described before, but you're then selecting the one which matches what actually happened. Okay, I've described the 5 laws of the improbability principle, but on top of this, we've got the human mind. I'll just give you one example of this. This is something called the conjunction fallacy. This is a description of a man. His name's John. He took a degree in maths, followed it with a PhD in astrophysics. After that, he worked in the physics department of the university for a while, then found a job in the back room of an algorithmic trading company developing highly sophisticated statistical models for predicting movements of the financial markets. In his spare time, he attends science fiction conventions. Now I have a question for you. Which of these is more probable? I'm going to give you 2 options. First, John's married with 2 children. Or second, John's married with 2 children and likes to spend his evenings tackling mathematical puzzles and playing computer games. Now, many people say B. The reason is because it's such a good match to this description. But B is a subset of A. So A must be more probable. That's just an example of how the human mind often finds it difficult to, I'm sure all of you got it right, but how the human mind often finds probability things counterintuitive. And there are many other examples. In fact, if any of you have read Daniel Kahneman's Thinking Fast and Slow, that book is about these sorts of things. Fascinating, and I recommend it. I'm not going to go through those. I'm just going to go through one example of something rather like it very quickly. This thing called pareidolia. Pareidolia is seeing patterns in random data. For instance, here's another example. This is an ultrasound scan. It's not a fetal ultrasound. It's not an ultrasound scan of a fetus. It in fact is a scan of a testicular cancer. So, and here's another example. This is a segment of the cosmic microwave background radiation, and there's this curious artifact in it. I don't mean the white ellipse, which would indeed be a curious artifact. Within that, there are, you can make them out when you can see this slide, the initials S and H. Clearly, Stephen Hawking. And you obviously got. I'm going to come back to cosmic questions in a moment. Oh, look, this is it doesn't just occur in clouds and vegetables. Rock face literally. Here's another one. Here's another one. And I can never resist this. These strange natural rock formations of Mount Rushmore. I don't know if you remember this. It happened a few years ago, about 5 or 6 years ago. The face on Mars. A space probe saw this. It caused a media, as you would expect, a lot of newspaper interest. Here's the same thing from a different perspective, and the face has completely vanished. It is just a trick of the light, just coincidence. And this is my favourite. This is Mother Teresa in a bun. Okay, so I've given you, I was going to say mundane examples, but maybe lottery wins and lightning strikes aren't mundane examples, but fairly sort of familiar human scale examples of the improbability principle. Let me move on. Evolution, the penultimate example of the improbability principle in action. 2 of the laws, the law of truly large numbers, countless billions and trillions of things evolving, developing in parallel, time, generation after generation down billions of years. The Earth's 4 billion years old. And then the law of selection applying to those. So evolution, penultimate law, a penultimate example of the improbability principle. I've said penultimate rather than ultimate because the ultimate example is the anthropic principle. There are various different versions of the anthropic principle. Some of them are quite frankly stupid and wrong. But the basic version is right. The basic version, you look at the universe and think, my God, if those constants weren't exactly as they are, we wouldn't be here. And you think, what an extraordinary coincidence. But the fact is, of course, if they weren't like they are, we wouldn't be here to see them. It's a classic example of the ultimate example of the law of selection. Okay, I want to conclude with a few slides showing you how to use the improbability principle. Is this okay? Thanks. When I wrote the book, when I was writing the book, the publisher said, yeah, but how can you use it? I mean, thinking clearly it was a business primer or something. I saw it as a book about how the universe works. But so I said, well, it isn't supposed to be a business. And then I thought, well, you can use it. And I'm going to give you a couple of examples. First, balancing probabilities. Okay, so I'm a statistician. I'm also a nerd. I have a large collection of dice. I really do. I have weighted dice, strangely shaped dice, spherical dice, which have sliding weights inside. And I have a dice with 100 faces. And these are 6 dice from my collection. If you look at these dice, you will see the white ones and you'll see black ones. I call the black ones my beginner's dice. And the reason I call them that is that in many board games, you need to throw a double 6 to decide who's going to start. It's very difficult to throw double 6s unless you're particularly skilled, 1 in 36 chance of getting it. So what I do, for instance, I give children a couple of the black ones and I say, practice with those until you can throw a double 6, and then we'll graduate. So they're my beginner's dice. Anyway, that was just a little story. What I'm going to describe is somebody picks a die out of a bag containing black ones and white ones, throws it 100 times without me being able to see, and all 100 shows, they tell me all 100 show 6. And they ask me, do I think the die is white or black? And I'm asking you, do you think the die is white or black? Well, you can do the probability calculations yourself. And what you're going to do is say, what's the chance of getting all 100 6s, all the 100s showing 6 if they're white? 6 to 100. Or if they're black, it's 1. And you're going to weigh the probabilities. It's going to balance the probabilities. This is just the law of likelihood. A standard statistical law couched in the framework of the improbability principle, if you like. Oh, here's another little example. This is a wonderful example of balancing probabilities. Arnold Schwarzenegger, he's a film star. He was a film star. In between, he was governor of California. When he was governor of California, this bill, 1176, came to him. He the governor has to sign off bills. If he doesn't sign them off, they don't get cast into law. And he was pretty pissed off with the people who sent him bills. He says, for some time now, I've lamented the fact that major issues are overlooked while many unnecessary bills come to me for consideration. Water reform, prison reform, healthcare are major issues my administration's brought to the table, but the legislature just kicks the can down the alley. He was pissed off with them, so he refused to sign it. He goes on to say, because of this, I'm not going to sign your bill. But what I want to draw your attention to is the first letter of this sentence, this line, which is an F, first letter of this one, which is a U, C. When his office was asked about this, they said, my God, what an extraordinary coincidence. But I ask you, balance of probabilities. Okay, what about bending probabilities? UK 649 lottery. Imagine buying one lottery ticket a week for 20 years. The probability of winning the jackpot, if you do the maths, is 2 in 26,893. 27,000, pretty small chance. But there's a way of spending exactly the same amount of money and having a larger chance of winning the lottery. Not much larger, but larger. And that is, if you buy the same number of tickets, 52 times 20, different tickets, obviously different tickets, but you buy them all in 1 week. You wouldn't buy the same tickets because that wouldn't increase your chance at all. So you buy 1,040 different tickets in 1 week. If you do that, the probability of winning the jackpot is just a little bit more. I could have picked numbers where the differences were bigger, but I wanted to keep these numbers simple. So buying all the tickets in 1 week, different tickets, increases your chances of winning. You're not going to win. It's a 1 in 27,000 chance of winning. So, you buy all these tickets in 1 week, and then you have to watch your friend who's buying one a week for 20 years, and he has the chance that he might win. So it reminds me of the International Lotto Fund, who set up this vast machine to buy their 7 million tickets. Each investor invested $2,800. They would have won Well, they did 10,800. But surely it takes away the fun of the lottery. You know, you might as well get a job, for God's sake. Anyway, let me come back to this. 52 times 20 different tickets increase your chance of winning. Obviously different tickets, I've stressed that, except for you've got to allow for the improbability principle. In April 2013, this man in California bought 2 British Columbia lottery tickets with the same number, and he won. What's particularly, perhaps irritating, ironic about this thing is that somebody else also won that week, bought the winning ticket. A woman bought it, and she must have really cursed Harry Black, who was so stupid as to buy 2 identical tickets. So she only got a third of the jackpot instead of a half. What about believing probabilities? Okay, this is the end. This is where I'm going to set you a test. How does the improbability principle explain why movie sequels are less likely to be big hits than the originals? One of the laws of the improbability principle answers that. Why US television programs are better when viewed in the UK, and UK programs are better when viewed in the US. The improbability, one of the strands of the improbability principle tells you that. And why the gambler's fallacy is wrong. The gambler's fallacy is this belief that, for instance, if you've got a fair coin and you toss it and it comes up 10 heads in a row, it's more likely to come up tails next time, because as we all know, a tossed coin will come up about 50-50, about half the time it'll come up heads and tails. So why is the gambler's fallacy wrong? And beyond. So that's the improbability principle, why extremely improbable events are commonplace. These 5 laws with the human mind and its problems in grappling with probability superimposed on top of it. That's it. Thank you very much indeed.
Here's my first question to you. Are you ever amazed by anything, given this?
I think that's a really nice question. Yes. I think people often say to me, okay, so you understand, you know, you witness, or somebody comes to me with a story of a highly improbable coincidence, very unlikely event, and do I just say, yeah, well, of course you'd have expected that because of this, this, and that? The fact that one can explain these things doesn't detract from the magic. And I usually illustrate this by talking about something in physics, sort of by analogy. The rainbow. You know, when you don't understand the rainbow, you see it arching across the sky and you think, my God, isn't that wonderful? Isn't that amazing? Isn't that incredible? But when you understand the physics, you understand how the light reflects and refracts around in the raindrops. It in no way detracts from that sense of wonder, that sort of magic. You still look at it and think, my God, and you stand and look at it, isn't that amazing? In fact, I would argue that understanding these things increases the sense of wonder.
If you win the lottery, you'd be euphoric, but you'd quite quickly sit back and think, I could easily do this again. Right?
Well, no.
Why? Tell me. I find this fascinating. This journey to writing this book, and I know you've written a lot of books, and EK mentioned the number of books you've written. Why did you write this book?
Yeah.
I mean, was it because you were sick of the oohs and ahs of people reacting to coincidence, and you wanted to explain to them that it wasn't so improbable?
No. The opposite, if anything. I mean, so I'm a statistician. I've worked with probability all my life, and it's very clear that people have problems intuitively grasping a lot of aspects of probability, as do I. I hope sort of, over the years I've begun to get a better grasp of a lot of it, but other things, sometimes I get things wrong. So it was an attempt to explain to people what was going on, why they should expect these things to happen, but also to convey the sheer thrill and excitement, the sort of anecdotes. There are a lot of anecdotes in the book, and some of the ones I've illustrated. It's still just as exciting. It wasn't that I was irritated or frustrated with people's lack of understanding.
Well, I guess let me ask the question a different way. Why did you feel a need to explain it to people?
As you will have guessed, I enjoy writing.
Right.
That's really what it was. I just enjoy writing, and with luck, and if I get it right, other people will enjoy reading it.
The 5 laws that you went through quite comprehensively there, which was this a sort of organic burn, this whole process, or was there a eureka moment when they all came together? Which came first? Which came second? What was the order for you?
Yeah.
When did you know that that's it, the 5 are done, before you started adding others, 6 and 7?
Yeah. That's an interesting question. Some of them, the law of inevitability, may not often be in the past been expressed in those words, but that's fairly straightforward. The law of truly large numbers does occur in odd statistical sort of, that expression, that phrase, that sentence, that name is used. So those already existed. The others, it was, I suppose I wasn't sure about the precise structure for all five until I actually was working on the book. But, people often ask me, how long does it take to write a book? And I say there are two answers. One is 6 months, you sit down and you write. And the other is 20 years, because you're accumulating, and this is a perfect example of that, accumulating stories, explanations, understanding, going back 20 years, and then you can start.
But could you, I guess that leads me to this question, could you 10 years from now be sitting there working on another book and suddenly think, actually there is a sixth law that I should have put into this book?
It's possible. At the moment, I think I've spanned the space. I would suspect that if there was a law which in some sense I'd missed out, it would be a relatively minor one. I think the law of truly large numbers, when you talk to people about this, the law of truly large numbers they may not have heard of, but they can understand, there are like 7 billion people in the world sort of possibly getting struck by lightning, this sorts of things. So the law of truly large numbers, the law of inevitability, are the ones which are obvious, come to mind, affect a lot of people, but people can relate to them. The others have a more minor effect. So if there was another law, a sixth or seventh law, it would be relatively minor, I think.
And the probability lever is probably the most complex of them all, would you say, for non-technical minds like my own?
It might well be, yeah. I can give you another example of that, which people might be interested in. So the Titanic, this is a straightforward example of the probability lever. The Titanic was mooted as unsinkable. And the reason it was unsinkable, it had, I think, 20 compartments all separated by waterproof barriers, so that if one of the compartments was damaged and flooded, it wouldn't sink. So it was described as unsinkable. But as you all know what happened. So the natural question is what happened, and the answer is the law of the probability lever. What happened was it was sailing through iceberg-infested waters. Icebergs, as you all know, 9/10 of the mass is below the water. They are big, heavy things, as indeed was the Titanic. So when an iceberg hit the side of the Titanic, it didn't just bounce off so that one compartment was damaged. What it did was gouge a great hole along the side of the ship, so 5 neighbouring compartments were all damaged. The fact that there were waterproof barriers between them didn't matter. Once one had been damaged, there was a very good chance that the neighbouring one would be damaged, and the neighbouring one, and the neighbouring one. So lots of compartments were damaged. The model on which the Titanic was based, this claim that it was unsinkable, was the wrong model. The circumstances were slightly different from what the people who designed and constructed it had said. So the law of the probability lever applied. It sank.
I'm an identical twin. I have an identical twin brother, and I was chatting with him yesterday about coming along to this, and he said to me, look, there must be a question in there somewhere for David about this. People ask us when similar things have happened to us in our lives. We're often asked, what has happened? Do you experience similar things when you're far apart? Do you dream about the same things, etc., etc.? Is there a something in there that could fit into this theory somewhere?
Yeah, I think there is. I mean, again, if you took two completely different people, they would be different in many ways. You will have similarities to your identical twin. You'll be inclined to behave in the same way. You'll probably have a similar sort of physical build and so on. So there will be similarities, so that it's more likely that you will behave in identical ways or do identical things than otherwise. So, the chance, one tends to sort of, you're comparing it with sort of two separate, completely independent people. So it's the law,
It's in there somewhere.
Yeah.
Are there different kinds of coincidences?
That's an interesting question. A lot of people, I've got a website where people can put examples of this, of coincidences which have happened to them, and a lot of people email me. And I think there are genres of coincidences. For instance, there are a lot of stories. In fact, my book opens with a story about a lost and found book. And I've come across a lot of stories about lost and found books, lost and found jewellery is another example. A ring which was lost, and 10 years ago someone finds it. The classic thing is the fairy tale, of course, in the belly of a fish, which I suspect has basis in truth because of all the stories the true stories I've heard. But there are other sorts of genres. Names. I kicked off with the true story about meeting this other David Hand at a conference. After that, I did the calculation, in fact, in the US. I can't get the UK figures. In the US, there are about 300 David Hands. And I did the calculation on how many conferences I go to, how many people are likely to be staying in the hotel that I'm staying in at that time. And it turns out, not at all surprising, that over the course of my life, so names are quite common. There's a classic story about a man named Frank Hughes who died, and his funeral was advertised, if you like, in the newspaper, announced in the newspaper, and people went along, and his friends went along, and afterwards they were astounded to see him walking along the street towards them. Turns out it was a different Frank Hughes. He was a merchant seaman, so that explained why the family had seen a lot of strange people at the funeral. And there are many. I think this is another genre of duplicate names coming up. Dennis the Menace is a really nice story. Dennis the Menace, comic character in the UK. The same week in the US, Dennis the Menace also appeared, but they're different Dennis the Menaces. They're different children. One has blonde hair, one has dark hair. They both have a dog, but the dogs have different names, and it was just a complete coincidence. Although perhaps, the improbability principle applies. Dennis the Menace is, if you're going to cause a sort of misbehaving little boy, what name would you come up with? Something like that. But I think there are coincident names is another genre of coincidences.
You ended by talking to us about how you might put this stuff into practice. I'm interested by your work for a hedge fund. For Reuters, I've done interviewed a lot of people in the financial markets. Is your job to make Winton Capital money, more money?
Winton Capital is sort of very much based on a scientific perception. What we do is try to understand the financial markets and other sources of data.
With the aim of making more money, surely?
Down the line, the pension funds who invest with us and so on want us to, they would prefer it if we made them some money so we can pay people's pensions.
And are you approached, again, it's probability, I think immediately of the insurance companies insuring against natural disasters, etc. Are you approached by a lot of insurance companies, reinsurance companies?
Yeah, while I'm working at Winton, I'm not, but I have worked with insurance companies in the past,
And final question from me, and then I'll let the audience have their say. Favourite coincidence?
Possibly my favourite coincidence is something which happened to me just after the book came out. This is a true story. I was contacted by a fiction author named John Ironmonger. You can go on Amazon and buy his books. He said, coincidentally, about the same time my book came out, he had written a novel called The Coincidence Authority in the UK, and in the US it's called Coincidence. This described a University of London academic whose partner also worked at the University of London and whose birthday was the 30th of June, which is my birthday. He said he'd never heard of me, never come across me, and hoped to use this coincidence to promote his book.
Very good. Right, let's have some questions from the audience. I know there was one over here.
I loved your talk, and it reminded me, speaking of brothers, my brother once pointed out to me that if we were very large, then relativistic phenomena would be intuitive to us. Yeah. And if we were very small, then quantum level phenomena would be intuitive to us. So I was wondering, what would we have to be like for probability phenomena to be intuitive to us? Very big memories, much wider experience.
Yeah. That's a very interesting question. And the reason that we often fail to have an intuitive grasp of probabilistic phenomena is our sort of evolutionary heritage. We've learnt to recognize patterns and make sort of predictions. We see movement in the grass and think a tiger's about to get us, or we recognize that certain plants are safe to eat. So I think there are the reason we behave as we do, flipping the coin 10 times in a row, expecting what will happen next, these sorts of things. So I suppose it's just our evolutionary heritage. Perhaps we'd have to be, I was going to say artificial intelligences, but I think even that's not true. If the AI is going to be in a robot which is functioning in the real world, it would probably have to have the same intuitive failures as we do, I think. So, yeah.
Thank you very much. There was another question.
A question about the coin. You pointed out interestingly, and in contradiction to most maths textbook, that there's heads, tail, and other. Now, I'm interested in other, because you mentioned, the coin could be slipping through the cracks, and there could be, it could be leaning against something on the floor. So I'm interested in this space omega, the space of all events that you need to define before you begin doing statistics. Have mathematicians ever thought about, how this process of defining this set omega at the beginning actually works, so that you make sure you cover everything? Are there any particular techniques? Because obviously there's more than heads and tails.
Yes, I suspect that mathematicians haven't, because in some sense mathematicians start by defining their universe. This is what I'm going to talk about. Omega represents all possible events. But I suppose other scientists, physicists or whatever, might say, and indeed my example would be, if you like, a physicist's example, could be heads or tails or land on its edge or lean against the wall or whatever. So maybe physicists are more likely to.
My old friend Aaron Sloman used to wear a bizarre hat with ear flaps. And his brother, Maurice Sloman, who used to work here at Imperial, chose the same hat on a different continent.
Just by coincidence, yeah.
Presumably they had similar physiologies.
This is the twin thing, isn't it?
Yeah, similar tastes.
My brother and I think, have similar
both in a cold
styles.
environment.
Yeah. Please,
I do have a website, the Improbability Principle, which allows you, if you have interesting or unusual coincidences, you can put them on there. And it would be good if you did, because I'm always building up more stories. And if they're great stories, I can introduce them in a future talk.
Last chance from the audience? Yep. Question at the back there.
Thank you. Very interesting talk. So how you compare your work with the work done by Nassim Taleb around, I'm sure, the probability of, you getting this question is very high.
Yeah. No, that's a good question. In some sense, you could say, and I half expected somebody to describe this as where Nassim Taleb went wrong. There's a professor at Brunel who is trying to set up a public debate between me and Taleb at the moment, where we can talk about these sorts of things, which would be jolly good if it went ahead. I'd look forward to that. But yeah, this is where he went wrong. This explains why he got it wrong, I think.
And that, I must say, that head-to-head between you and Nassim would be certainly one to watch. Anyone else?
I find interesting that you didn't start out by defining what probability means.
I didn't.
I wonder if you could define it now, actually.
Okay. So you can look at probability in various ways. You can describe the mathematics of probability, and mathematicians would do that. They would set out axioms and say, as I answered to this other question, that's my universe, and I'm going to work out the consequences of these axioms and so on. But that's not really the interesting thing about probability. Well, not for a statistician. It might be for a mathematician. For a statistician, the interesting thing is what probability means, how you interpret these axioms and the objects described by the axioms. And there are different kinds of interpretation. You're probably aware of, subjective interpretations, frequentist interpretation. There are different ways of interpreting probability, which are different ways of looking at the world. They might be one of these ways will say probability is out there. It describes a physical property like solidity or whatever of things in the real world. The others, other kinds of perspectives say probability doesn't exist out there. There's a famous quote by a man named from Bruno de Finetti, which says probability doesn't exist. It's all to do with your understanding of things, your beliefs, your knowledge about things, and how you manipulate that understanding. It doesn't describe a concrete sort of reality. And there are other ways of thinking about what probability means. Now, it's not a question of some of these being wrong and some of these being right. They are different, if you like, interpretations of probability. And I do talk about those a bit in the book, but I was going to say, you could write a whole book on that. Well, many people have written whole books on what it means, and I deliberately try to not go too deeply into that in this talk, certainly, and indeed in the book.
But what would be a best way to model uncertainty, given, if you have to attempt to understand, how to capture that uncertainty value? Is it Bayesian a right way to do it? Or, what would be your recommendation for that?
You mean, is your question really, am I a Bayesian? Or
Maybe.
My answer is that just as you remember, or you're probably aware of George Box saying no model is right, but some are useful, I would say that different approaches, different schools of inference, and they're not just Bayesian and frequentists, there are others. Indeed, there are many different kinds of Bayesian schools. Different approaches to inference are suitable for different kinds of question, different kinds of problem, and you need to work out what question you're answering or attempting to answer before you decide how to approach it. So I'm eclectic.
Final question from me. What book are you working on now? What do we have to look forward to, David?
Many of you will be familiar with the very short introduction series that Oxford University Press produced. They're very short, they fit into a pocket. I wrote the statistics one, and I'm now working on one on measurement. Measurement is something which has fascinated me for a long time. I wrote a big, moderately technical book on it 10 years ago. I originally started in the hard sciences, in mathematical physics, where you measure things like weight and length and speed of light and things like that. Then I spent 10 years at the Institute of Psychiatry working on psychological sort of questions, measuring IQ, preference, opinion, these sorts of things. And over the last 10 years, I've spent a lot of time working with government on discussing how you measure things like GDP and inflation and unemployment and things like that. But you'll see that the common word, the common theme underlying all this is the word measurement. But it's pretty apparent that measuring IQ is very different from measuring weight or length. The word is the same. So I got fascinated by to what extent they were the same thing, to what extent they were different, what are the implications for how you analyze data from these different measurement processes and so on. And I described a lot of that in my book 10 years ago, and now I'm writing this very short introduction.
And it reminds me, actually, I forget which country it is that has the happiness index.
Bhutan, you're thinking of. Yeah,
that's right.
Yeah. But lots of countries, the UK is developing one, lots of countries around the world are developing, not a happiness, a well-being index. Happiness and well-being are different. But, yeah. And in many cases, not an index, but a profile of different measures. Yeah. Bhutan is the one which tries. Bhutan has got sort of questionable human rights record and figured that, this is probably a way of coping with some of the criticisms.
Thank you very much indeed.
Thanks very much indeed.